What's up? This video covers section 5.5, the substitution rule. Often we call this the U substitution or U sub rule because typically we use U as our letter of substitution, but obviously it doesn't matter what letter you use. The point of this is to essentially do the chain rule backwards when we're taking antiderivatives of more complex functions. So for a quick example here, if you look at 2x e to the x squared, if we just had e to the x, we can handle that. E to the x squared with the 2x in front of it makes it more complicated because we can't split this integral up into two pieces because we have multiplication. Right? For addition and subtraction, you can split it up, but multiplication and division, you can't. So what we do instead is we try to reformulate the problem using a U substitution. And essentially we're going to simplify it by doing some tricky substitution, take the antiderivative with our new variable U, and then get back to what we started. For an example like this, and in general, what you want to look for is making your U the thing in the complicated place. Like here, like I said, e to the x we could handle, e to the x squared or e to the 3x plus 5. If you have a complicated power in your e or a complicated expression like under square root in the denominator inside of another function, think chain rule backwards, right? That's usually going to be your u. And the second thing you look for is if you pick a u, like let's say I want x squared to be my u, does my du show up in the problem? Du is the derivative of whatever your substitution is. If I substitute x squared as my u, then du is 2x. See how we have a 2x? A 2x dx we will call du. So typically you know if you're on the right track if whatever you pick for u, your du, or the derivative of that, is also in the expression. So in this case, if I let my u be x squared like we talked about, then the derivative of u, or the derivative of x squared, would be 2x, and since we're taking the derivative of x now, we put a dx. So our job now is to turn 2x e to the x squared dx into something just with u's and du's. Our job is to get rid of all of the x's. So have we accounted for everything? We have e to the x squared, which we can call e to the u, because u is x squared. So this piece here becomes e to the u. And then the 2x dx, this whole thing is just du, right? It's the derivative of x squared, which we call 2x dx. So if we just write e to the u, we're taking care of this piece, and then du, we're actually taking care of this piece and this piece. So we can turn this whole problem into this problem, antiderivative of e to the u, and we know that an antiderivative is just e to the u, so then, well, plus c, and then we can do a substitution and get it back in terms of x squared. So let's look at an example. So here we're going to try to do a substitution, and remember you want to pick your u as the thing that's in the complicated spot. Right now what's complicating this is the fourth power, and the fact that we don't just have x to the fourth. If this was x to the fourth we'd be fine, but we have x squared plus 1, and that's making it a little bit more complicated. So we're going to try to choose this as our u, and if we choose right, our du should show up in the problem. So if you want to choose x squared plus 1 as u, then the derivative of that du would be 2x dx. And notice that piece is right here too. 2x and dx, that piece can be taken care of with du, and then instead of having x squared plus 1 to the fourth, we'll have u to the fourth. So once we make this substitution, this is what our new integral looks like. We'll have u to the fourth, and then we'll have du. And like I said, this piece here, we want to account for all the x's in the problem. This piece becomes u to the fourth, so that's taken care of with this piece. The 2x and the dx, those are literally equal to du, so we're replacing that with du. So this takes care of all the x's in the problem, and now we just have to integrate u to the fourth, which we can do pretty simply with the power rule, which will give us u to the fifth over 5, and plus c. And then for our final answer, we'll just write it back in terms of x's, because x is equal to x squared plus 1, because u is equal to x squared plus 1, we have x squared plus 1 to the fifth over 5 plus c. And that is our final answer. And as always, you should be able to check that and see that its derivative is what we started with. That last problem was considered a perfect substitution because what you picked for your u, the du, showed up exactly in the problem. Sometimes your du isn't exactly what you have in the problem, but it differs by a constant or a sign, and we can correct for that by multiplying or dividing by constants in order to kind of fix it and make it work. So for example here, we want to pick a u that's in the complicated place, and right now we have we have an expression inside the square root that's in the denominator. Notice if you pick u to be the 1 minus 4x cubed, the derivative isn't exactly in the problem. The derivative would be negative 12x squared. We have 2x squared instead, but notice that differs by a constant. Right? We still have x squared, which we can work with, and we can just change around the constant in front. So we'll make our u substitution as 1 minus 4x cubed, and then our du, the derivative of that, would be negative 12x squared dx. And like we said, we have an x squared dx in our problem right here, but we don't have a negative 12. Instead, we have a 2. Now this 2, for example, we're actually just going to pull out of the square root, or pull out of the integral and deal with that later. This negative 12, we can kind of do the same thing right here. Let's just solve this for x squared dx by dividing the negative 12 over to the other side. Then we'll get du over negative 12 equals x squared dx. So here's what our new integral will look like. We'll have the integral, and first of all that 2 is going to be out front, and then on the denominator we're going to have the square root of u, right, because the 1 minus 4x cubed is our u. The x squared dx, let's just put a 1 on top, the x squared dx is going to become du over negative 12. And let's make sure we've accounted for everything. This 2 comes out front. The square root of 1 minus 4x cubed becomes the square root of u. It's in the denominator. And then this piece, the x squared dx, that whole thing is equal to du over negative 12. So I just kind of pulled that out to the side. But they're all being multiplied together, so it's all the same thing. If we simplify a little bit, we can pull the negative 12 that's in the denominator all the way out front with the 2 and simplify it to negative 1 over 6. Right, that's our negative, that's 2 over negative 12. And then we have the integral of 1 over root u du. And we're almost ready to take the antiderivative. The only thing we should do first is write that as a power. So 1 over square root of u is the same thing as u to the negative 1/2 du. And then we can take the antiderivative with the power rule. So the antiderivative power rule says increase the power by 1 and then divide by that new power. We already have a negative 1/6 out front. If we increase our power by 1, we'll get 1/2. And then if we divide by 1/2, remember that's the same thing as multiplying by 2. So it looks like we end up with negative 2 over 6 u to the 1/2, which negative 2 over 6 reduces to negative 1/3. And remember, u equaled 1 minus 4x cubed. So this becomes negative 1/3 times 1 minus 4x cubed to the 1/2. And you could leave it like that, or you could also, the 1/2 power, oops, don't forget, where's our plus c? Right up here. Our constant, plus c. And then we could write it as a square root if we wanted to. Negative 1/3 times the square root of 1 minus 4x cubed plus c. And that would be a good final answer. Here we're going to solve a couple definite integrals using u substitutions. And the main difference is that when we change our variables from x's to u's, we need to change our bounds from x values to u values. To start the substitution, notice that we're over cosine squared, which is our complicated piece. And if we let u be cosine x, then du will be negative sine x dx, which is almost what we have on top, except for the negative. If we just divide that or multiply that over, though, we can write it as negative du equals sine x dx. So when we go to rewrite our integral now, on the denominator we have u squared. And if we pull the negative, this negative right here from the du, if we pull that out front, we can write this as negative the integral of 1 over u squared du. Now before we change the bounds, let's make sure we have everything. Cosine squared, that becomes u squared. So we have u squared on the bottom. The sine x dx, remember we solved for that and we got minus du. So that minus we pulled out front, the du is right there. So we've accounted for all the pieces that was in our original problem, except for the bounds. Now our substitution says u equals cosine of x. These are x values right here, so when x is 0, we get cosine of 0. which equals 1. So our new bound down here is going to be 1. Right? It's going from the x value 0 to the u value of 1. And then when x is pi over 4, we have cosine of pi over 4, which is what, root 2 over 2. So that'll be our top bound, root 2 over 2. Okay, so that is the main difference when you're doing u substitutions with definite integrals. You have to remember to convert whatever your original variables are. Once you do your substitution, you use that substitution to solve for your new bounds. When x is 0, cosine of 0 is 1. When x is pi over 4, cosine of pi over 4 is root 2 over 2. Now we just continue with the integral. These are all u values now, so we can just get an answer in terms of u, which will actually be the same answer if we left it in x. This will be equal to negative, let's just change, instead of 1 over u squared, let's change it to u to the minus 2 du. And then we're ready to find our antiderivative with the power rule again. So using the power rule here, we'll get, keep the negative out front, we'll get u to the negative 1 when we increase it by 1, and then we divide by negative 1, and we evaluate this from 1 to root 2 over 2. The negatives will cancel out, and u to the minus 1 we can just rewrite as 1 over u, evaluated from 1 to root 2 over 2. And so when we plug in root 2 over 2, we get 1 over root 2 over 2, minus when we plug in 1, we get 1 over 1, which 1 over root 2 over 2 we could just call 2 over root 2, and 1 over 1 is 1. That's a perfectly good answer. You could rationalize the denominator or get a common denominator or get a decimal approximation, and they all should be the same thing. Here's another example of a u substitution where we need to change the bounds for a definite integral. Here, if we make our u x squared plus 1, which is the piece in the denominator, then our derivative will have an x in it. It won't be exactly x, but at least we can take care of that x on top. So if u is x squared plus 1, du would be 2x dx. And we have the x dx, we don't have the 2, so let's just divide it by 2. Du over 2 equals x dx. So our new integral, it will be over u. Let's just make it 1 over u. The x dx will become du over 2. I'm going to go ahead and pull the over 2 part out front. There's 1/2 out front, so that's the over 2. And then we'll just keep our du to the side. Let's make sure we accounted for everything. X squared plus 1 on the denominator, that is our u, so there's our x squared plus 1. And the x dx is equal to du over 2, so the 1/2 part I just pulled out front because it's a constant, and the du part's right here. So together the 1/2 and the du account for the x dx. To change the bounds real quick, notice when x is, when x is 0, we have u equals 0 squared plus 1, which is 1. So our bottom bound will become 1. And when x is 4, u is equal to 4 squared plus 1, so that's 16 plus 1, which is 17. So there's our new upper bound. Let's take the antiderivative. You might be a little rusty. The antiderivative of 1 over u is natural log of absolute value of u from 1 to 17. Okay, so we took our antiderivative. Now we're ready to evaluate. If we plug in our upper bounds, we'll get 1/2. Let's just actually factor out the 1/2. We'll get natural log of the absolute value of 17, which we don't need those absolute values anymore, then minus the natural log of 1, which we still don't need the absolute values there. We have 1/2 times, natural log of 1 is 0. Right, so that piece goes away. So we actually just have this times the natural log, and again, don't need the absolute values, and that is our answer. Right, again, you could get a decimal approximation, but that's pretty good. Okay, we're going to do one last example of substitution. This is a trickier, slightly more advanced substitution, but there are a couple of these on the homework, so I figured I'd show you some of the other things you can do. This problem, you probably want to make your u substitution x minus 4 because it's in the denominator under the square root. The problem with that, though, is the derivative of x minus 4 is just dx, and we actually have another x on top. So it's not your typical kind of the du staring right at you kind of problem. But if you follow your instincts and let u be x minus 4, then our du would be dx. That's true. Now what we can do is we can write this as the root u, and our dx will be du. The question is, what do we do about that other x on top? Well, if you take your du equation and actually solve it for x, let's just take this off to the side real quick. If you solve this for x, you can add the 4 to the other side, and you can actually get u plus 4 equals x. You see that if you take this equation and add 4 to both sides, it cancels out over here and you get x. It adds to the u over here and you get u plus 4. So this will actually let us rewrite an x, a single x, with a u plus 4. And we can put that on top now. Right, so we have accounted for everything. The root x minus 4 becomes root u, right on the bottom. The du and dx are the same because the derivative of u is just the derivative of x. This one's 0. And the x, we were tricky a little bit, and we played with our u substitution, solved it for x, and got an expression just in terms of u and a constant. Now, at first glance, it may not look like we've simplified much. However, now that we have just one term in the denominator, we can do this. We can split up the fraction, or the numerator that is, over the denominator, and write it as as two separate pieces. We can actually find the antiderivative in just a sec now, because u over root u, if you think of those as powers, it's u to the 1 over u to the 1/2. That will give you back a u to the 1/2. When I think of u to the 1 over u to the 1/2, you subtract 1 minus 1/2, and you actually get u to the 1/2. And the second piece, we can call it 4u, and since we only have one u in the denominator with the square root, it'll be actually u to the negative 1/2. If you notice, now since these are two separate pieces and they just have u's to powers, we can use the power rule to find our answer. So now if we take the antiderivative using the power rule, we'll increase the power by 1. This will be u to the 3/2. And then when we divide by 3/2, it's the same thing as multiplying by 2/3. And same idea with the second piece. We have plus 4. It'll be u to the, when you increase it by 1, you get 1/2. And then when you divide by 1/2, you get the same thing as times 2. Don't forget your plus c. And if we just simplify a little bit, we'll get 2/3 u to the 3/2 plus 8 u to the 1/2 plus c. And if I recall correctly, our u was x minus 4. So we have 2/3 times x minus 4 to the 3/2 plus 8 times x minus 4 to the 1/2 and plus c, which I barely fit in there. And that would be our answer. So again, it's just a u substitution, but it's a little bit trickier because you have to play around with it to accommodate another x that was floating around in your problem. It's a little bit less of a common type of substitution, but I figured I'd show you it. That's pretty much it for 5.5, so send me an email, let me know if you have any questions.